You know, for some reason, people think that dealing directly with the file system is insanely difficult. Oh, C++ incorporated Boost file system, an abstraction layer that essentially prevents direct manipulation with the file system. But I'm going to show you how easy it really is. Yo, welcome back to the development diary of Umi, the new systems level language that I think will one day change the world. Last time we were in the middle of reading in the files underneath this examples directory here, and we're looking for all of the files that end in this umi extension, but I stopped short of doing the recursive step. Right now, all this code will do is it will look in the very first layer of examples, but I need this to also recurse down into the various folders and pull out files that are embedded inside of there. And that's basically the focus of this video. So let's just dive straight into it, shall we? So the first thing is that we haven't explored all of the different members inside of our directory entry iterator here. Actually, there is dname, but if I pull out my handy IntelliSense, you'll see there's also, well, there's the dname length, the I number, the record length, seek offset, but there's this type variable here, which, based on the name, I guess you can tell that we're going to use this to determine the type of this file. Unfortunately, if I go and quickly look at the documentation for, this is quite bright, that's nice. The documentation for dtype will show us that we're looking for dt as this file thing being a directory, but only some file systems will support this. So we're going to have to handle that. And I guess what I'm thinking of doing is we will assume that if this type data member doesn't equal to dt unknown, then we'll just accept it as a directory. And if it is unknown, we'll have to use lstat, which is another system call to figure out the type of the iterator that we're holding. So let's just basically write that code. We'll just directly write it in. So we said now if the string that we're looking for ends in .umi, then we'll read this in. So this is kind of like our base case, right? Because eventually, not even eventually, I think we need to do this now. So we're going to be recursing into our folders. To me, the easiest way to do that in code is to just write a recursive function. So let's pull out this code into its own function, shall we? What shall we call it? Let's call it order POSIX read source strs. Or maybe get sources, actually. We'll start there. So usually when I pull out a function from somewhere in code, I leave the parameters empty and the return type is void. And I want the compiler to tell me the problem. The problems with the function, so that way we can fix up the name. So as you can see, first thing we need is a sources root, so we'll put that in. So we need a const char star sources root. And I guess we'll pass that in directly here. Yes. So what we'll do is, well, actually, we also are putting stuff into our compilation thing. So let's put stuff, let's pass in this compilation module first. So this was a compilation module. We'll call this compilation modules. Definitely not using camel case. Compilation, call it compilation. Awesome. What else is next? So sources root, let's call the sources root dir, actually. And then this source root is a string, which we initially passed in, for us, it's a constant. So if I just fill in this call right here, pass in the compilation. I think I called it umi compilation, actually. Sorry, my mistake. Right, that makes a lot of sense because we're passing in the compilation and it's like holds all of them, and any single compilation unit is a compilation module. So we pass that in. Also, we'll pass in source root here. And We'll do this like that. And I think as for the call site, this is good enough. All right, this might actually be all that we need to do, and I'll show you why. So we've got our, will essentially become our return value. This is an input and an output. And we also have the directory that we're recursing from. So the very first thing that we'll do is, if you remember from last time, we had the problem that when we try and do, where is the call? POSIX read entire file here. This dname that we get from the directory entry iterator is just the base name. But from the perspective of the program, we start executing from umi project. And then if we want to read main.umi, it would have to be examples/main.umi. But to encode the full path, because the POSIX APIs, they don't let us pass in a list of paths. It has to be just one single string. So to avoid, where is open? So to avoid having to create a brand new file name every time, instead what we can do is we can just change the working directory every time we go into one of the subdirectories of the source files here. And if we did that, then we wouldn't have to allocate any extra memory. So that's what we're doing. So we can start off our POSIX get sources by just changing the directory into the root directory. And then at the end, when this function is about to return, then we just jump back to the place that we previously were, right? Because on POSIX, every single, I think even on Windows this works, every directory has a hidden like dot member, which represents the parent, and dot, which means like the current directory. So we can just use this to our advantage because the file system is already implicitly a tree. We don't have to do anything special, right? So we change the directory into where we're going, and we'll, since we've now changed compilation to be a pointer, we'll have to fix up our pointer stuff as well. Whoops. We'll have to fix up the way that we access this, which is really annoying. This is like the worst part of pointers in C++. When you go from a struct straight to a pointer, you have to fix up the syntax. But I mean, a lot of people have problems with this. Here's the reasons why the arrow syntax is good. Here's the reasons, right? If everything was just a dot, for example, if I had made umi compilation a reference rather than a pointer, then you suddenly, implicitly inside of your mind, start treating the pointer as if it was there on the stack with you, like a regular struct. And that seems like it would be harmless, but if you have a massive struct and you're accessing members from many different places, then you run the risk of like accessing members and having cache misses because the things are really far apart. For our struct, we don't have that problem. But for massive structs, that becomes a problem. And personally, for me, I just like to know that what I'm dealing with is a pointer. And I like that to be reflected in the syntax that I use to access things. So personally, I'm all for the arrow syntax. But when you go from a struct value to a struct pointer, there's a bit of pain. All right, cool. So we just pulled out this function. Let's reap the benefits of doing that. So with our if statement here, what we'll do is we'll just stick an else here first. And we'll say if our iterator's dtype is equal to dtdir. I'm pretty sure that's what this was. Yep, that's right. If the dt type is equal to dtdir, else if, so this is building up. Here is where we'll need to do the stack thing. The lstat thing, I should say. Actually, you know what? Probably we could collapse this. So let me rephrase this. So if now the dt type is dtdir, then we'll do something. Else, if the dt type is unknown, here is where we'll have to do an lstat. So we'll say, do I already have one? I don't. So we'll call this st. And this is a struct stat. And we want to do an lstat. Now, lstat takes in a char star, which is what we have. We have the dname, which is a char star. Well, actually, no, this is a char array, but it will degrade into a char star. And we have our return value, which is st. Now, if st's type, I actually don't remember how to check the type from when you do an lstat. So let me quickly build up the check the documentation for this. Let's see here. It would be really nice if it just had a list of all of what the members do. It probably does somewhere, I just can't see them right here. All of these system calls return a stat structure. Yeah, it's probably this. The file type and mode, so it's st mode. This field contains the file type and mode, see inode 7. Great. Stat.st mode, see the discussion of file type and file mode below. Okay. File type and mode. So we want directory. Let's see here. So the st mode field contains the file type and mode, refers to the bits corresponding to the mask. Okay, so it looks like it's just a mask. Or we could, yeah, it's just a mask. To test for a regular file, then we, and the mode with this thing to block out, I guess, the something to block out stuff that is unrelated to the file type and mask, and we want to check if it's equal to isdir. So let's just grab this quickly, our little template piece of code. Okay, let's see. If our st mode ended with that special bit masking thing is equal to, in our case, dir, then we'll do a thing. Sweet. So what are we going to do? Well, what we're going to do is we're just going to call this function again. We'll do get sources, but this time we'll do it with, again, compilation, and then name. And we'll just grab that and put it there too. So let's just like mentally execute this code before we do it. So we start here. So we start executing from Umi project, come down here, jump in. We're passing in the sorcery, which for us was examples. Yep. Jump in, change the directory to examples, start reading. Ooh, there's a bug. Open dir. See, what's cool about this now is when we open the dir, we've already moved the current directory to where this was just pointing. So I only need to say dot when we open the dir because we've already we've moved relative to our target. So we open the directory, then we start iterating over the stuff. Probably eventually what we'll need to do that I haven't done yet is close dir. Anyway, so we'll start executing over stuff. We'll come down here. If we have dt-dir, then we're basically doing the same thing, but now this name, which for us will eventually be stdlib, should drop us into the same place. We'll then change directory to stdlib, and then the cycle repeats. So this looks like it should do the right thing. But to be super sure, what we'll do is we'll run the program. All right, jump in. So source root dir examples, that's what we expect. Change the directory, looks all good. Looks like we got a pointer back, so that's cool. Skip, what are we at? What is this? This is, let me add a watch variable so we can see. So we're at dot, so we'll skip that. And we have dot dot, we'll skip that, come down, Where are we? We have stdlib. Great. We have a directory. So we'll jump over this one because it's not a directory. Was this filled in? It was. Okay, good. It's always extremely satisfying when the case that you want to test comes up immediately. So we'll jump in now. Sources root dir is stdlib. We changed the directory to stdlib. Looks like that was okay. Maybe, hopefully. We open. We got a pointer back, so it looks like it's okay. We read. What do we get? Probably we'll have dot and dot dot first. So we'll just skip that. Skip that. Okay. Studio.umi. Perfect. And that is the file inside of here. So it looks like it's doing the right thing. And this will probably, resize. Good for us. We'll read the entire file. I may have, if we look at now compilation, module 0. What do we have? Just the source iter. You know what would be really good is we should also keep the name inside of here. So I think we'll also add that in. Where is umi? There we go. Maybe the original file name, or actually we'll say module name, like this. Now, if this is going to be a string, we want to keep it as a string. For the time being, I guess what we'll do is we'll actually just have this inline as like a 32, a max 32. But then we'll have to store the name length as well. No, what we'll do is we'll have this be a max of 32 characters, and then the end of the string, we'll make it like a C-cell string, where the end of the string is a null terminator. Since I don't believe, like, it should be impossible to have a null terminator in the middle of a file name anyway, so that should be okay. Yeah, so what we'll do is we'll come back up here, and we'll definitely read the entire source file there, and do we have a strict copy? We don't. So let's make strict copy quickly. String copy is a really, really easy function to write. So we'll say context per order, str copy, like this. You're right, C++, they have like copy, stud copy, and they do it like source dest. But I've always kind of viewed this as dist and then source like this, because this follows the same order as the assignment statement, like the equal sign. And to me, this just seems right in some weird way. And we'll have this return a char star, which is really easy. We'll just have it return. Ooh, how do we want to return this? Like this. So what we'll say is size under t n equals 0, and then for n is equal to 0, while source of n, then we'll increase n, and dest of n will be equal to source of n. And at the end, what we'll do is we'll actually return an iterator or a pointer to the end of dest, because sometimes it's useful. Sometimes it's really useful when you have this dest thing be an expression. At the call site, it's an expression, and you want to save the result of the expression at the end of the string, so that way you can like chain copies. And I've always found that kind of pattern very, very useful to have. So we'll have the return value just be dest plus however many characters we wrote, and we will return that. I guess there is one more way we could make this. We could write it like this as well. Let me rewrite this quickly. We could say while star source, and then we'll do star dest equals star source plus plus. This is like a very, very, very terse way to do the same thing. And this works because plus plus, the way the compiler reads this is it reads it like this. So it will do dist ++, so it will move the pointer by 1, but this is post increment. So the return value of dist ++ is what dist was originally, but as a side effect, dist, the destination, will be moved by 1. So ultimately, the effect of this is that we will move dest by 1, but the original value of dest will be dereferenced. And it's the same thing for source. So this has the effect of copying source of 0 into dest of 0 and then moving both pointers along by 1 to the right. And since we've now moved this as far as we can to the end of source, the final value of dest will be dist plus that counter that I had before. So this is kind of a very, very terse way to do the same thing. But it's okay. So we'll say string copy, and what are we copying? We are copying. Now that we've done that, actually, I'll need to do this. This is now compilation, modules, compilation, and modules. I guess we can do the same thing. We can do compilation and modules ++, module index, module name, and URDT name. And we have a problem here. What have we done wrong? Let's see here. So module name, what have we done? No matching function call because something is not a char star. Are you not a char star? You are a array, and you are an array. So what's the problem? No matching function call. Huh. Let me see here. Is it thinking that this is just a straight array? Is it, if I cast this to a char star, will it fix up? Yes, it will. Usually arrays should decay into, oh, because this is const, that's why. My mistake. There we go. Okay, fixed. Yeah, so the reason why is because you can't, this did decay into a pointer, but it decayed into a const char star. But obviously we're modifying it, so that's not legal. It's not legal at all. All right, cool. So let's just rerun this code again and see what we get. I'm expecting that we have 2 modules, which we do. And let me just do compilation.modules name studio.umi, very good. And also main.umi, very good. And probably if we look at the source, this looks like the source. And what about you? Just a single line. You also look like the source. Wow, is this really 36 characters? I guess it could be. 3, 7, yeah, I can see that being 36 characters. Okay, looks like our code is all good. So that leaves us now in the perfect position to start parsing in the very next episode of Umi, the new systems language that I hope will change the world. So, awesome. So the thing that we did today is we went over how to do directory type checking or file type checking with Durant or OpenDir or whatever this thing is called. Yep, Durant for POSIX platforms. And we also took a little peek into how to do some cool string functions. If you think string copy is cool. I mean, you might think this is pretty bland, but I mean, it's good to know how to write the basic things yourself, right? This didn't take long. How much was this, like 60 seconds or something? Didn't have to import anything. Didn't have to do anything. So, cool. I'm happy. So, thank you so much for watching, and I'll catch you in the very next episode. Take care.